Okay, so recording has started. So today we have our second talk related to ArkLib, after last week's talk on the library itself. So this week we have Katie, who's going to talk about the work that went into implementing coding theory in ArkLib, which was very much from the ground up because there was nothing in MathLib other than, I guess, a bunch of stuff about having distances before us. So Katie has a PhD in maths, then found herself doing cryptography at Nethermind, and then found herself doing form verification at Nethermind, and is currently now a postdoc at Imperial College London with Kevin Buzzard doing mathematics in Lean, and is still obviously contributing to ArkLib and will be doing more coding theory related work in ArkLib in the next couple of months. So we'll probably revisit this in a few months, I expect. Floor is yours.
Thank you very much. So first of all, the work I'm going to present is done by a lot of people, as I will explain. And since I didn't know who was going to come to this talk, we're going to start with just a general overview again of what's ArkLib and so on, and then progressively move into more technical things, and we'll see how technical we get because of time. So yes, ArkLib is, well, probably most of you came to Kwong's talk last week, but even if you did, a reminder is that ArkLib is a library that is basically the aim is to formalize in Lean everything needed for formalizing cryptography. And it's not only formalization in terms of just formalizing something. The idea is to make it modular and more composable. So we want for all definitions for the protocols and so on, we want them to be broken down into pieces in such a way that when new protocols come up, for example, it would be easier to build them from the jigsaw pieces we already have. And yes, the same is true for definitions and for whatever is needed to formalize cryptography. And of course, the goal is for ArkLib to become the go-to library for that. It's like, I like to say it's in my vision, it's going to be the ArkLib for cryptography. And of course, the project is funded by the Ethereum Foundation, and it's part of the verified zkVM program. So currently, ArkLib has around 20 contributors, actually exactly 20 contributors. It was a guess. I had a guess when I wrote this slide, and I checked before the talk, and yeah, we have exactly 20 contributors, approximately 7 to 8 regular contributors, but of course, it would be great to get more and more contributors, and I think we're definitely getting there. Yeah, so the next slide is really because I didn't know who's going to attend. So what is Lean? Lean is a programming language and an interactive theorem prover. And as I mentioned, it's one of the biggest libraries in Lean currently is MATLib. And this is also the largest repository of mechanized mathematics. So MATLib is very interesting because as we'll see later on in the talk, for some easy, in my opinion, things such as matrices and linear algebra, there isn't much, but if you need some higher level maths like category theory, things are escalating and there is a lot of content. I suppose it depends on the interest on the people who are writing and PRing into MATLib. But yes, the point is that the content varies, the difficulty varies, and because it's an open source project, people are contributing with, like, the contributions are in line with the people's interests. Yeah, so Lean, of course, it works with, it's a dependent type theory based language, and the idea, I mean, all of these formalize, the kernel is reviewed by thousands of people because, of course, if you formalize something incorrectly and then you use it for proofs and so on, things are going to break. So it's as secure as it could be, as correct as it could be, and it really helps get to the bottom of the mistakes in mathematics, I would say. So yeah, because of this, it's the perfect solid base you can want to formally verify the cryptographic protocols and any cryptographic things you might need. So yes, now we get to ArkLib. So as I mentioned already, everything we want to formalize in ArkLib, we want to formalize it in a modular way and break it down so we could reuse it. So there is also, it's not only about just getting a bunch of cryptography and adding it to ArkLib, it's about planning and thinking what's the best way forward. And if you attended Kwong's talk, you would have learned a lot about the idea how to break SNARKs down. For example, they're represented as IORs, interactive oracle reductions. And yeah, this fits this the whole idea and the whole vision that things should be as efficient and as reusable as possible. So I mentioned MATLAB already. It's one of the main dependencies because cryptography uses a lot of mathematics. It's probably hardly a surprise to anyone. And we're not going to be developing absolutely everything from the ground up unless needed. So, of course, we're using MATLAB heavily wherever possible. And the other main dependency is VCV-IO, which is another library for basically deals with probabilistic computations needed for cryptography. And it's also a very interesting place. I haven't actually explored it as much as I should have, but yeah, the interactive oracle reduction probabilistic backend, so to speak, were imported from there. So if people haven't looked at it, I highly encourage for them to take a look as well. And yeah, as far as coding theory goes, as Alex mentioned in the beginning, there was like MATLAB virtually contains no coding theory. There were Hamming distances, I suspect, just because there is quite a bit on general metric spaces and distance functions. So it's not so difficult to go from there to Hamming distances. But for example, there is a lot of missing linear algebra. I'll get to that in more detail when I do the walkthrough of ArkLib. But yeah, whenever there is something missing, we need to formalize it in order to achieve the goals of ArkLib, right? In order to be able to formalize whatever cryptography we need. The other thing which we did at Nethermind while I worked there, we did quite a lot of explicit constructions with bivariate polynomials. So in MATLAB, there is a univariate polynomial library, which contains a huge amount of lemmas, definitions, and yeah, whatever. But the main things you would need would be there. And there is a separate multivariate polynomial library. But for example, in coding theory, it's quite useful to have explicit constructions on bivariate polynomials because a lot of protocols use bivariate polynomials explicitly in one way or another. So having a way to reason about bivariate polynomials and having the equivalent lemmas, definitions, and so on is quite useful. And one thing which I think we don't have at the moment, and in my opinion would be very useful, is to develop in Lean algorithms for factorizing bivariate polynomials. There are a few of those in the literature, but even the Henzo lifting algorithm, for example, is not fully formalized in MATLAB. So there is a Henzo theorem of some form, but the explicit algorithm is not there. So yeah, there are many things like this which are missing. And even though, as I mentioned, there is a general multivariate polynomial library which deals with polynomials of n variables, these constructions, so factorizing polynomials of n variables is a very difficult mathematical problem. So we can't expect for there to be any like formal algorithms to do that. But with bivariate polynomials, there are a couple algorithms that are tractable. And having such a thing in ArkLib, for example, I think would be a very good thing. So we could prove some constructions from basically with Guruswami Sudan and with it's needed for the soundness of Fry, but I'll get to that in a minute. Yeah, and I already talked about VCVI. What else did I miss? Oh, yes, another thing which I will probably mention now is since I'm talking about polynomials, the polynomial libraries in MATLAB are non-computable, but Nethermind started this computable polynomial library that has now just been moved to, I think Derek is working on it and Alex. So that's going to be expanding. So we have a model of computable polynomials anyway at the moment, which is great for the purposes of ArkLib. So what else is there in ArkLib? So there are basics of coding theory. I'll show you some concrete examples and hopefully we can go through everything there is, but I don't know how long that would take. Yeah, so therefore there is a formalization of these IORs, interactive oracle reductions, which Kwong talked about last week in great detail, so I'm not going to go over everything again. And yeah, this is the modular abstraction for interactive oracle proofs. Then other interesting things. So there is a formalization of Fry in ArkLib, of SumCheck, Binias, Basefold, and KZG. I think KZG is ongoing because there was something with the Lagrange interpolation in the computable case. So Fry, the formalization of Fry is non-computable at the moment, but the plan is to make everything computable. So once the computable polynomial library has expanded, there are things that need to be added to it as far as I understand. It would be made another dependency of ArkLib, and all of these models of these, the IOPs would become computable, which is needed if we want to formally verify just the real life implementation against them. So yes, the other thing in ArkLib is there is a detailed blueprint of the proximity gaps paper for Reed-Solomon codes, which is one of the main papers that deals with the soundness of Fry. In particular, is the soundness of batched Fry. I will also talk about this later, hopefully. There are also blueprinted statements of stir and whir. And there is also a lot on interleaved codes now. I believe these are results from the proximity gaps in interleaved codes paper. And yeah, I already mentioned about us working to add the missing mathematics from MATLAB and so on. So what are the future plans? So of course, we want to continue enriching all the theory, and there's still quite a lot of coding theory. It's quite interesting because even in cryptography itself, a lot of definitions there are slight variations between them in different papers. So if we want to be able to reuse definitions and to have this sort of homogenized theory appearing in ArkLib, we need to find the best language to express the cryptography. And of course, this is not going to be useful only for us, but generally it's a good thing for the research community as well to have a set definition as like the base standard to go from, because then all these deviations that could lead to errors would be eliminated. So the next thing, as Alex mentioned, which hopefully I'll be working on from next month, would be these proximity generators definitions, which would definitely help homogenize a lot of the theory. But I'll show you an example later why this is needed. So the next steps in terms of IOPs would be the implementations of stir and whir, which are really the important IOPs at the moment, so to speak. So Fiat Shamir and the BCS compiler are also planned for the future, and we need those because, as I mentioned, with Fry, with base, fold, stir, and whir, they're all implemented as interactive protocols, but actually you need them to be non-interactive. So this is the whole point of Fiat Shamir and BCS compilers. You compile the interactive version into a non-interactive version, and combined with the computable polynomial library, this would enable just checking real life implementations against the formalized versions of all these SNARKs. So also, as I mentioned, a lot of the cryptography theorems, lemmas, and so on related to proximity gaps. Well, I haven't really mentioned the exact ones, but there are a lot of theorems and lemmas, especially related to the soundness and completeness of the Fry protocol, which are sorted out. So proofs of these would be needed, and we want to get to a point where there are no proofs missing, because if we want to be able to actually prove something is secure, we need to have no gaps. We need to check everything works. So all these proofs need to be added to ArkLib, and that's not only, I mean, I'm mentioning Fry because this is the main work we did at Nethermind. But yeah, there is also other blueprinted statements, I believe. And the goal is to make ArkLib sorry-free as soon as possible. And of course, at some point in the future, it would be nice to also add zero knowledge, so we could make the SNARKs ZK SNARKs. And yeah, I kind of touched upon this slide. Maybe I should have put it earlier, but coding theory. So we're going to focus on coding theory. That's the whole point of this talk, to understand what coding theory we have in ArkLib, what coding theory we need to develop. And why do we even care about this? Well, we mainly care about this because coding theory has become really popular in modern cryptography, and it is the base language of the IOPs that are used in industry, and these are the basis for the cryptographic protocols that underpin the ZKVM. So we really need to prove these secure to make sure that that they work as expected and that everything is as secure as possible. And also the good thing about coding theory, in my opinion, is that it's easier to understand. So all this linear algebra is much more approachable, even by, like, you don't have to have a PhD in something to understand linear algebra. If you have enough background to do Lean or to read cryptography, you can understand linear algebra 100%. So it's, in that way, it's more approachable in comparison to, for example, elliptic curves, right? If you want to do elliptic curves-based cryptography, you really need to have some more serious number theory background. Yeah, so the ease and the approachability are quite nice, and also it's post-quantum secure, which also is really good. And I'll actually skip this slide because Kwong already talked about it. I added this for completeness, just yeah, so we can recall what IOPs are. But okay, maybe I'm not going to skip it. I'll just go over it very quickly. You have two parties protocols with a prover and a verifier. And the prover knows the witness, and he wants to convince the verifier of that the relation, which is a subset of the statement and the witness, is true. So he wants to convince the verifier of the truthfulness of the statements. And so the focus of this talk, because this relates to coding theory, are those IOPs, which are a subclass of IOPs, where basically you assert that the witness is delta close to a code word. So you can see already code words means we have a code, a big spoiler, and delta close implies there is some distance at play. So yes, finally, the plan now is I'll give a very intuitive definition of a code in case people haven't worked with codes before. And then I'm going to show some definitions, and then we're going to see the formalizations and then explore what else is there in ArkLib. So coding theories now it's become popular in modern cryptography, but it's actually, it's not a new thing. It has roots in telecommunications, error correcting codes for telecommunications, and some other there are a lot of other usages as well. So you've got what is really the setup. You have a sender who wants to send a message, let's say a message of K symbols to someone, but it's over a noisy channel, which means that errors could be added to this message. It could get corrupted to some extent. So the sender encodes this K symbol message into N symbols. This accounts for the number of errors we're kind of adding, in a sense, allowing to be added, to be precise, sends it over the channel, and the N symbol message is our code word. And the receiver receives this code word. And now you can see there are two processes. There is the encoding of the message, which makes the K symbol into the N symbol, obviously K is smaller than N. And there is also the reverse process of decoding, which is you get your N symbol message and you want to understand what was the original intended message. So in symbols, how do we do that? So we have a finite alphabet, sigma, let's say of size q. These are, you can think of these as the letters that you use to construct your message. So the code is a subset of sigma to the n. This means that the message has length n, right? This is n tuples of words. You can think of this as, if you want, a vector with n elements, or just, you can think of this as a word in n letters, or however you like. And C, the elements of C are the code words. N here is the length of the code, because each element of your code has this length, and K, which is in the general case, when you're looking at just a code as a subset, it's log Q of the, well, this should be sigma. Yes, and this is the dimension of the code. Yes, I have a typo, it's normal. But we're more interested in linear codes. So what's the difference? The difference is that, again, we have a finite alphabet of size q. This is usually, so always, so if you have a finite alphabet of size q, you think of this as a finite field of q elements, where q is a power of some prime p. And a linear code this time is not only a subset, but it's a vector subspace of fq to the n. And once again, n is your length of the code, and k is the dimension of C as a vector space over fq. So here you have the nice thing, when you're looking at linear codes, you have the nice thing that your fqn is obviously a vector space of dimension n, and C is also a vector space, right? It's a subspace of your ambient space. So this, actually, I want to skip to this, then I'll go back. This is nicer in a sense, because it helps you think about, it helps you reason about the codes in an easier way. What I mean by this is, because you're in the world of spaces and subspaces, you have, for example, if I want to think of the encoding and decoding functions, I have more tools. Well, generally, when I have vector space as opposed to just subsets, I have more tools from linear algebra, and you can already see the linear algebra is kind of entering the picture. But even from the intuitive definition of a code, we mentioned that we have two main functions to think about. We have the encoding and the decoding, right? So the encoding is the function of taking your K length K, so K letter message, and making it into an N letter message. And here, so FQK is obviously a vector space of dimension K, and C the subspace of FQN. So your encoding actually becomes a linear map. And if you, well, from linear algebra, you probably know, if you've done linear algebra, I'm always assuming people have, you know that linear maps could be represented as linear maps or as or by a matrix. So you have this matrix corresponding to every code, which is called the generator matrix. And sometimes you say the code is generated by this matrix G. And you can, this extra layer of having a matrix associated to the code allows you to do some nicer, well, I would say calculations, but it helps you prove some results more easily sometimes. And we're mainly interested, so we've specified from a general code to a linear code, and now we're going to specify even more to the codes we care about most in Freister and WAR, which are the Reed-Solomon codes. So what is a Reed-Solomon code? You have your alphabet is again FQ, finite field of Q elements. The next piece of information you want is an evaluation domain, which is essentially you pick n distinct points in FQ. So obviously n is less than Q. And your Reed-Solomon code is the evaluations of all univariate polynomials. So these are polynomials in just one variable over the with coefficients in the finite field FQ of degree at most K. And you evaluate at every point. So that's how you obtain your n tuple at the end. So you have in the intuitive picture, what is the initial message is the polynomial of degree less than K. And the corresponding code word to that polynomial is you take your polynomial, you evaluate it at the end points, and this is how you obtain your n tuple. So the set of all of these is our Reed-Solomon code, and we're going to denote it. Oh God, I have another typo. So this is supposed to be FQ, DK, right? This is the evaluation domain, and this is the degrees of the polynomials. So in a minute, we're going to move to ArkLib to see how all of this is implemented. And I don't know, maybe we can just do it now. Or let's look at the Hamming distances as well to understand. So the last piece of the IOPs, you had in the general, very high level, very, very high level of your picture, you had a code. And we were talking about being delta close to a code. So we've seen the formal definitions of codes, linear codes and RS codes, which are the three things we're going to care about. But we haven't really clarified what it means to be delta close. So of course, to be delta close or close to anything mathematically, it means you want to have a distance function. And the distance function you use in coding theory is called the Hamming distance. So you take 2 points in your code, and the Hamming distance between them is the number of positions on which they differ. And obviously, if you want to, so then the distance of the code itself is the minimum Hamming distance overall x and y in the code, where x is not equal to y. So you just calculate all the pairwise distances, find the smallest one, and this is the minimum distance, or sometimes just called the code distance. There is another distance, which is the relative distance, and this is just literally your distance of the code divided by the length of the code. The good thing about this relative distance is that it's between 0 and 1, so it is the distance used in to state a lot of the security, soundness results, and so on. So we understand everything. Well, and proximity, you can guess. It means that the distance between 2 points is less than or equal to delta, where delta is some real parameter, and you can pick this distance to be the Hamming distance, or you could pick it to be the relative Hamming distance. Of course, if it's the relative Hamming distance, you need an extra bound on delta to be less than 1, because the relative Hamming distance never is between 0 and 1. Okay, so now we have gone through all the basic things. I'll come back for that in a minute. Let's see how these codes and distances appear in ArkLib. So now stop presenting this and try to share the GitHub, see what happens. Right. Can you see ArkLib?
Yep.
Yes.
All good.
Okay, great. Thank you. Okay, so if you go on ArkLib and you want to understand where everything is in terms of coding theory, so you click on ArkLib and then data and then coding theory, right? So you can already see there are a lot of files. So in the basic file is where you can find the basic definitions, and there are these very nice descriptions of what exactly is in the file. So for example, the first definition that appears is the definition of Hamming distance of a code. So a code is just a set, right? This is not a linear code. This is just any code. And this is how the definition looks like. There is, yes, another thing I forgot to mention is we have tried to do in coding theory, we have tried to do everything in the most general version possible. So what I mean by this is, for example, you can define distances for codes. They don't have to be linear codes. So we haven't restricted ourselves to the linear codes. Right here, we could have chosen C to be a linear code, which would have been modeled as a submodule rather than a set. So whenever that's not needed, we don't do it. This is how it's done in MATLAB as well, even though MATLAB sometimes takes it to an extreme. So you also have the notion of distance from a code. So you have your code C, you have a vector, which is just a vector or an n tuple if you're just a code rather than a linear code in the space, and you calculate at how many points does this vector differ from the closest element in your code. So as you can see, when you have a definition, it's good to have a few lemmas to actually, first of all, to check that you're doing what you think you're doing as a sanity check, and also to see that things behave as you would expect, right? So here we have a lemma that the distance to a code is at most the distance to any specific code word, so you're not actually going crazy. And yes, you can see there are a lot of results on distances. The good thing, of course, is that, well, I'm not going to go through this proof, but the good thing, of course, is that since the Hamming distance is a metric, and there are a lot of results in MATLAB on metric spaces and just general distance metrics, by having this definition, you can reuse the MATLAB results. So whenever you want to use some property, some well-known property, I don't know, like triangle inequality or something, you don't have to reprove it. You just use MATLAB for that. Or sometimes there are some similar definitions in MATLAB and similar formalizations that you could reuse. I'll show you an example if this has not changed in the last 3 months or so. So we have the Reed-Solomon codes, right? Our most used codes for the time being. Maybe things would change in the future. And we have evaluation of a polynomial of a set of points as we expect. We have our Reed-Solomon code. See here, the output type is a submodule because it's a linear code, right? And it's important for this to be a submodule because we want to also, for the Reed-Solomon codes, we could, there is a very nice generator matrix corresponding to the encoding function. And this is the non-square Vandermonde matrix. So this is an example of something that wasn't in MATLAB. I think now they have it, or it was PR'd. I don't know whether they merged it. But at the time when we wrote this, I think it was, I don't know when it was. It was April this year or May this year. When it came to the Vandermonde matrix, MATLAB only had it as an n by n matrix. But since we were dealing with a subspace of dimension k in an n-dimensional subspace, you need a k by n matrix, which is non-square. So we used the MATLAB formalization and just changed it slightly to make the square matrix non-square, and then reproved the things that were proved in MATLAB for square matrices for non-square matrices. So MATLAB was helpful, even though it didn't have the exact thing we needed at the time. It was still helpful as a base for the mathematics that was needed for finding the generator matrix of a Reed-Solomon code. So we have the theorem. See, there's some theorems about ranks of non-square Vandermonde matrices, which of course you can't expect in MATLAB since there was no non-square matrix in MATLAB at the time. But it was very interesting because in the process of doing all of this, we also discovered that there were not many results on row and column spaces, the row and column dimensions of a matrix, which was, at least to me, it was very surprising because I just assumed at the time, of course, I mean, this is something you study in first year undergrad, it's going to be in MATLAB. But yeah, there wasn't, so we needed to add those in the preliminaries file as well. And eventually we proved that the generator matrix of a Reed-Solomon code is a Vandermonde matrix. So this is the lemma in question. So this is quite useful because, as I say, sometimes you want to flip between thinking about the encoding map as a linear map, or you want to use the matrix for some specific calculations. And yeah, you can find in the preliminaries file, there are things that were missing from MATLAB, for example, or just basic notions you need throughout the coding theory part of ArkLib that are not, they don't really belong anywhere because they're not coding theory, they're just some generic mathematics. And yeah, we put them in the preliminaries file, and I think this is now sorry-free, which is really nice. Also, let me see. So interleaved codes I mentioned, I'm not going to explain what they are, but just roughly speaking, you've got you can think of the words of the interleaved codes as matrices where each row is a code word. So yeah, this has increasingly grown throughout last year. They're not only there in the beginning, there was just a definition of an interleaved code, but then Chung did a lot of work on interleaved codes and yeah, this proximity of interleaved codes paper that I mentioned earlier. So here we've got loads of results on that too, and I also think those are sorry-free at the moment. And another thing, since I'm on the topic, which I mentioned, was we talked about the encoding function in detail, but it's also interesting to think about decoding. And decoding is a much more difficult problem generally because what happens is, as you can guess, you get a you just see the final message, the message of length n, and you want to understand what was the original k-length message that the sender intended to send over the noisy channel. So for Reed-Solomon codes, there is a very nice decoder algorithm called Berlekamp-Welch, and you open this. So Ilya and František did this in ArkLib, so you can find this algorithm, and it's very is very nice because the way it works is you receive your evaluation of your polynomial, and then you have this error parameter, and the error parameter is obviously the maximum amount of errors you're going to allow in your code. So the algorithm goes as follows. You construct a polynomial of degree at most your error parameter. And from there, you could reconstruct the initial polynomial that you use for the evaluation. And it's all done in ArkLib, in the Barlecam-Welsh. However, there is this now caveat of things missing in MATLib again, that as part of the algorithm, you want to be able to solve a system of linear equations, which of course you have a matrix of some size times a vector equals another vector, and you want to find the first vector, right? The solutions. But MATLib doesn't really have Gaussian elimination. Well, doesn't have Gaussian elimination. So you can see in the source file here, there is the linsolve, which is exactly finding a solution to the system of linear equations. We need to do it to be able to have the full Barlecam-Welsh algorithm. Okay, then there is a more complicated algorithm decoder, which I mentioned earlier, Guruswamy-Sudan, and this is also blueprint. So this is blueprinted actually. It's not fully proved as bar the linsolve as Barlecam-Welsh. But the Guruswamy-Sudan is slightly different. First of all, slightly more difficult. It deals with bivariate polynomials, and I did mention earlier that we don't have the algorithm of factorizing bivariate polynomials, which is needed. And also, it would need to solve systems of linear equations as well. So two things are missing. One of them is important. The linsolve is really important for both decoders, but yeah, the factorization is important for Guruswamy-Sudan and also for proving some proximity gap results for Fry. So let me actually go back to my slides and go back to the other. Okay. So let's just, in the last, I don't know how many minutes, 10 minutes, we can look at proximity gaps, which is, so the proximity gaps properties are, we're talking about distance preservation in a sense and how close you are to the code. So let me give the general definition and then I'll explain the high level picture, since I've already talked for quite a long time, it seems. So the proximity gaps definition, as it appears in the proximity gaps for Reed-Solomon Codes paper, this is your mathematical definition, but roughly what it asserts is that if you have a property which is just a subset of sigma to the end, where sigma is a finite set, so you can already see this is under the hood, this is going to be some code. And you also have another collection of sets inside the same ambient, well, I would like to call it a space. You have a distance measure on the ambient space, and you say that your collection of sets displays a proximity gap. So you've got two parameters, delta and epsilon, with respect to your initial set, if every element in your collection of sets is either delta close to the code, or there are only a small number of elements that are delta close to the code, right? So you don't deviate too much. And you call delta the proximity parameter and epsilon the error parameter. So as one could probably guess by the name, in the proximity gaps for RS codes, you have this beautiful theorem that if your property P, which by the definition we could have guessed is going to be a code of some description, So if P is a Reed-Solomon code over FQ with evaluation domain D, size n, and your polynomials you're evaluating are of degree at most k, and if C, the collection of sets, is actually a collection of affine spaces in the vector space of dimension, this is supposed to be size of D, but yeah, n, because you know size of D is n, then the affine subspaces display a delta epsilon proximity gap to the Reed-Solomon code with respect to the relative coming distance. So you have exact parameters for delta and epsilon in the paper, and they're split into two cases. You have a delta in the unique decoding radius with the corresponding epsilon, and then different numbers up to the Johnson bound. And this is crucial in establishing the soundness of batched Fry, which is basically, Julian is going to talk about Fry in, I presume, a great amount of detail next week. Probably about batched Fry, I don't know. But in Fry is a low degree polynomial test, and you test one polynomial. In batched Fry, you test n polynomials at the same time. That's why it's called batched, right? And to prove, actually, the main theorem that proves the soundness of Fry is the theorem in the proximity gaps paper, which proves soundness of batched Fry. There are more papers on the round by round soundness, which is a different kind of soundness. Probably Julian is going to talk about this, but I don't know. I don't want to say things I don't know. And to establish the soundness of batched Fry, you really need this proximity gap result. And this is proved by using three main theorems. And then they've got weighted versions, but I thought adding those in the talk is going to just be a bit too much. So you've got correlated agreement over affine lines, over curves, and over affine spaces. And these things then get weighted with certain weight function, then you use them to prove soundness of batched Fry. So we've got all of these statements of these theorems from the proximity gaps for Reed-Solomon code paper, formalized in ArkLib. I'm going to show the code very quickly in a second. They're sorted out for the moment. There are no proofs, but we really want to prove them as soon as possible, so we have full end-to-end formalization of Fry in its soundness. And let me actually show these, and then I'll see whether I have time for correlated and mutual correlated agreement, because I just thought I would have more time.
We could go a few minutes over time as well, if we need to.
Okay. I'll be very quick. I spoke too much about MATLib, I think. So, yeah, there is a proximity gap file, and you can see, so there's some proximity gaps properties of, that's the paper we want to look at. So here you've got the delta epsilon proximity bound that I talked about, right? So you have, generally the epsilon, the error bound depends on the proximity bound delta, which is why when you look at the definition, you have your delta as an input, and then epsilon depends on where your delta ends up, right? Because the delta would be, this is the splitting case of if you're in unique decoding radius, which means are you close enough to the code that when you try to decode, there is only one code word you can hit, or are you in a slightly bigger radius, which is there might be a list of code words that you can hit. This is the high level picture of the distinguishing cases here. Yes, so this is the first theorem I showed you on the first slide, that Reed-Solomon codes display delta epsilon proximity gaps with delta and epsilon as stated here. And then you've got theorem 1.4, which is the correlated agreement over lines, which, as I said, so this theorem, then correlated agreement over affine curves and affine spaces. These three theorems, their proofs are sort of the meat of the soundness of Fry. And we really need to get them in order to then prove their weighted versions. But I think the weighted versions appear in the same section. The formalizations were done by Ilya, so I just want to give proper contributions to who wrote what. So there is also some Guru Swami Sudan stuff that's needed along the way, as you can see. But yes, there would be weighted versions somewhere here. They were in the section 6 of the paper, if I remember correctly. And yeah, as you can see in this file, because we really did the blueprint of the paper, most things are sorted out. So we have to get all these proofs in very well as soon as possible, really, to make things sorry free. But yeah, you can see there are a lot of statements to get to the weighted versions as well. And yeah, these are the proximity gaps. Let me now show you the correlated and mutual correlated definitions, because this would kind of show the final point of why we really need to homogenize the definitions along in the literature. Okay, so I just said what's correlated agreement. Very quickly, if you have a code, the high-level idea of correlated agreement is, suppose you have a code. Suppose I take, I have a Reed-Solomon code, F1 and FL are polynomials that I want to be evaluating. And suppose I take a random linear combination of these polynomials. Here you can see. So the random linear combination, I'm not taking each field element for my linear combination individually. I'm picking a random field element and then doing powers as a coefficient of each polynomial. So if this random linear combination agrees with a code word, this is supposed to be small c, agrees with a code word in my code on S positions. S is a set of size at least 1 minus delta times the size of the evaluation domain. So if this random linear combination agrees on size of S positions, then you can find a set T inside the evaluation domain, which is also a dense set, but not the same as S, such that each F would agree, after being evaluated, would agree with a code word on T positions. But you can see the S and the T are not the same. So your random linear combination agrees on a certain number of positions with the code word, and each one then individually would agree on a certain number of positions. But then there is a mutual correlated agreement, which is a stronger property. More or less, you've got the same idea, with the caveat that actually S and T are the same set. So you can already see why it's stronger, right? Because if the random linear combination agrees on these positions, then each word has to, each evaluation of a polynomial has to agree with the code word on the exact same position. So you have a very coherent and nice picture. And the reason I'm showing you this is, first of all, because it's very interesting. And second of all, this is very important for proving we're secure. There were a lot of papers recently on showing mutual correlated agreement for RS codes. There is this whole thing which Alex could explain with the proximity gaps conjecture and so on. Ethereum is giving a price out of $1 million for it, whoever can prove it. But to even formalize the statement, we're in a bit of a situation, because this is one definition of correlated and mutual correlated agreement. Then you can get another definition of mutual correlated agreement through something called the proximity generator. And there are different types of proximity generators. They're polynomial, they're powers, they're univariate powers, they're non-polynomial. So for us to be able to, then there is something called a strong proximity generator, and so on. So for us to be able to even state the conjecture and or state any security result involving mutual correlated or correlated agreement, we need to have a unified definition of what it means to have a correlated agreement, right? We can't say, oh yeah, in this case it means this, in this case it means this, and then have 10 different definitions in Lean and in ArkLib. So this would be the next thing, hopefully, that I'll work on to formalize. There is a new paper called on proximity generators, and hopefully we could get this with the unified language, and then we could express the security of thrive, stir, and war with the unified language, and this would help not only ArkLib and our proofs, but also it would be helpful to just for the general research community to have something expressed in the same language. Because I mean, in maths, I deal with this every day. There is this definition of something, and I just don't know, is it the first version or the second version, or so on. The other, I showed you all of this. Yeah, we did this. And the conclusions is, yeah. I've gone over everything. So thank you very much for listening. And I hope this was somewhat clear. And if you have any questions on anything, please let me know now or afterwards or wherever. And yeah, thank you very much.
Yeah, thank you. I'll leave a minute or so if anyone has any questions. And then otherwise we can obviously stop the recording and leave it here, and then it'll be up on YouTube in a few hours, I guess. So yeah, if anyone has any questions, you can unmute or type them or anything like this. And then otherwise we can call it. So I have one question actually, which is aside from the proximity gaps and mutual correlated agreement and generators and everything around this, from the statements that were formalized, which ones were unexpectedly, tricky to formalize in terms of being misstated or, having some undefined behavior in the reference paper or something like this?
Oh, from the ones we worked on.
Yeah.
Oh, there was this whole deal with I don't remember the exact statement, but this, the Guru Swami Sudan part of the proximity gaps paper, which heavily used what they call Appendix A. And there was a lot of Kenzo lifts and some strange coefficient rings going around, a lot of rational function fields. And this was unexpected. Some of the components were very tricky to get to. I remember there was this definition of a determinant as well. We had to contact the authors to see exactly which version they use, and actually the version they said they use is not a version I had ever heard of before. So that was an interesting experience.
Yeah, the choice of formalization. Okay, I see Derek has his hand up.
Hi, Katie. Thanks for the great talk.
Thank you.
I had a question about toward the end you were mentioning, I think it's proximity generators that have various definitions. Is there a sense in which these disparate definitions are equivalent or roughly equivalent? Like, are these kind of special case definitions, or are they kind of notionally the same idea, but there isn't an obvious way to prove their equivalence?
So for these ones, I think because they're new definitions. The first one, the first time I saw it was in the war paper, and they just used a specific polynomial powers generator. But then because this is it's just a random function. Essentially the idea is, how do you pick the randomness for the linear combination for the mutual correlate agreement definition or correlate agreement definition? So as I showed on the slide, there was only one field element that was picked, and then you did powers. That's what they call now the power generator. I think there wasn't the language wasn't really developed at the time. So then in subsequent papers, people thought, okay, actually we could also do this or also do this. And now there is this new paper on the polynomial generators, unifies everything that was done before, gives a very general definition, and then lists all the other definitions that appeared as special cases. And on the basis of this, you could then restate the mutual correlated, the correlate agreement, and so on in the language of the new definition. and make it more general, which is exactly what we want in ArkLib, right? Because we want to have a general case, then we can instantiate in a specific case.
Yeah,
Rather
that makes
than
a lot
have
of
this
sense.
fragmented picture. Because initially the univariate powers was called the proximity generator, but then something else was called the proximity generator. And
We had there were a few issues in the original work on formalizing. Some of the were statements had an issue due to basic confusions about this, which were then kind of fairly easily solved. But I think we're mostly down to parts of the paper and parts around the proximity specifically being introduced without much intuition, which made it easy to then make mistakes.
Yeah, and there was then this subsequent paper. I think it came almost immediately after Warp, was it? Where
yes, they use a different definition in Warp.
Yeah, there was a different definition. I think this is where I took the strong proximity generator from, because the proximity generator was then renamed to a strong proximity generator, but it was the same thing. And then the mutual correlated was stated differently. So it becomes unless we unify the whole language, it becomes intractable to know what's being used. And I think now it's early enough that we could influence this. Even with formalization, we could influence it. Whereas when you do it in mathematics, sometimes it's just been years and you have to watch the change.
Okay, then I guess if there are no other questions, then we're slightly above the hour, so it's probably a good time to call it. But yes, thanks for the good talk and the good work. And I guess maybe once we've unified the definitions in ArkLib, we can come and revisit this. In a couple of months.
Thank you.
All right, I'll stop the recording.